In this lecture, we first are going to talk about eigenvalues and eigenvectors of symmetric matrices. Then we will talk about quadratic forms and positive semi-definite matrices. In addition to this, we are going to talk about how we can determine whether a matrix is positive semi-definite by looking at their eigenvalues. All right, so there are two remarkable properties when we talk about symmetric matrix. Such as A, which is an n by n matrix. First, we can show that all of the eigenvalues, of this matrix are real. So they are all real values. And the second one, the second property is eigenvectors of a symmetric matrix are orthonormal. So before we define that. So what does this mean? This is equivalent to matrix X, which is defined as x1, x2, xn is an orthogonal matrix. What's the reason for this? Because the columns of this matrix X are eigenvectors of matrix A. And we talked that eigenvectors of matrix A are orthonormal. So if you look at the previous lecture, in that lecture, we said that matrix A can be represented by X, matrix of eigenvalues, lambda 1 to lambda n 0, 0, and X inverse. But in this case, for symmetric matrices, what we are going to do, we are going to represent X by the symbol U. And because this matrix X is orthogonal, then X inverse is X transpose, or U inverse is U transpose. What does that mean? A before was X, matrix of eigenvalues, X inverse. Now what happens? I replace X with U, and I replace X inverse with U transpose. So this is the new representation of matrix A in terms of its eigenvalues and eigenvectors in the case where A is symmetric. So this feature helps us in the future for simplifications and for some of the optimization methods that we are studying. So using this, we also can talk about the definiteness of the matrix and the sign for its eigenvalues. But before getting into that, I'm going to talk about definiteness, semi-definite, and positive semi-definite, and positive definite matrices. All right. In order to do that, we start with definition of quadratic form. So given the square matrix A, which is a real matrix, and it's n by n, and given a vector like x, which is n by 1, the scalar value x transpose A x is a quadratic form. So x transpose AX, if we expand this, this is equal to sigma I from 1 to n, sigma j from 1 to n, a ij, xi, xj. Also, if we want to simplify that further, x transpose ax is equal to x transpose ax transpose. What's the reason? Because this is an scalar. This is just one number. So we can find this transpose and it's equal to the original value. Is x transpose a transpose x is equal to x transpose a plus a transpose divided by 2x. So just an example to understand this, let's say your number is 2. 2 is equal to 2 transpose. Because this is 1 by 1, this is also 1 by 1. So now we build on this quadratic form to define positive definite, positive semi-definite, negative definite, and negative semi-definite matrices. So 1, positive definite. A symmetric matrix like A is positive definite if for all non-zero vectors such as x, so A is n by n, x is n by 1, x transpose ax is greater than 0. Note that this is a scalar value, so this is just a number. And when a matrix is positive definite, we show that with this symbol. 0. Similar to this, we can define positive semi-definite. Positive semi-definite matrices. So a matrix, a symmetric matrix, such as A by symmetric A n by n is positive semi-definite if for all vectors like x, which are n by 1, x transpose ax is greater than or equal to 0. So if you look at the previous definition for positive definite, it should be absolutely greater than. But here it can be greater than or equal to. In this case, we show A is positive semi-definite. You can have the same definitions for negative definite and negative semi-definite. So A n by n, which is symmetric, is negative definite and denoted by a less than 0 if for all vectors x n by 1 x transpose ax is less than 0. And finally we can define negative semi-definite. So for a, which is n by n, and for all x which are n by 1, if x transpose ax is less than or equal to 0, in that case, we call this matrix negative semi-definite. So you may ask, where do we use these notions, right? So what's the application? If you recall, when we were defining convexity, we referred to positive semi-definiteness, positive definiteness, negative definiteness, and negative semi-definiteness. So that's why we need to know these definitions and then use them to realize whether a function is concave or a convex. So an interesting observation is if matrix A is positive definite, then minus A is negative definite. This is very similar to definition of convexity. So if function f is convex, then if we want to find this matrix like this is f of x, then this is going to be minus f of x. So if you can see, the convexity of f and minus f are at the other side. They're vice versa. Another observation about positive definite and negative definite matrices are always full rank. So if they are full rank, it means they are invertible, and you can find their inverse. Another interesting fact is, given any matrix A, which is n by n, it's not necessarily symmetric, not necessarily symmetric. So given this matrix, we define matrix G as A transpose A, and sometimes we call it the Gram matrix. This is always positive semi-definite. Also, if m greater than or equal to n, so if m is greater than or equal to n, then G is equal to A transpose A is positive definite. Also, we have to make an additional assumption, which is A is full rank. So G is always positive semi-definite. But if these two conditions hold, m is greater than or equal to n, and A is full rank, then it's positive definite, which is a very strong condition. All right. So there is another way to understand whether our matrix is, our symmetric matrix is positive definite or negative definite. So how do we do that? Matrix A, n by n, which is symmetric, is positive definite if all eigenvalues are strictly positive. Strictly positive. So let's say I give you a matrix A n by n. First, you find its eigenvalues lambda 1, lambda 2, lambda n. If for all I from 1 to n, lambda I is strictly positive, then your matrix is positive definite. Using the same definition, matrix A n by n, which is symmetric, it's positive semi-definite. If all of its eigenvalues are non-negative. So which means lambda I is greater than or equal to 0, then your matrix is, we can say matrix A is positive semi-definite. And we can follow the same definition for negative. So if lambda i's are strictly less than 0 or strictly negative, then your matrix is negative definite, your symmetric matrix. And if lambda i's are non-positive, in that case, A is negative semi-definite. So this is one way to identify whether a matrix is positive or negative, definite or semi-definite. So in this lecture, we talked about eigenvalues and eigenvectors of symmetric matrices. Based on this, we showed that a symmetric matrix A can be represented as U vector of eigenvalues, matrix of eigenvalues, U transpose. This is equal to X vector of matrix of eigenvalues, X inverse. Then we talked about positive and negative definite matrices. And something that we mentioned, if eigenvalues are strictly positive, then A is positive definite. If they are non-negative, then A is positive semi-definite. If they are strictly negative, A is negative definite. And if they are non-positive, then A is negative semi-definite.